So today we are going to see a simulation of a shock absorber system using MATLAB Simulink. So let's get into the question. Model a simplified shock absorber system using Simulink. The system consists of a mass attached to a spring and a damper. Apply a constant force to the mass, set the mass m, spring constant k and the damping coefficient c to simulate an underdamped system and then an overdamped system. Plot the velocity and displacement responses for both the cases. So now we have to simulate a simplified shock absorber system. So before getting into the problem, let us see what the system equation is. So this system equation is nothing but this is the equation in which the problem depends on. So we are going to write the equation of a simple spring system. So spring with a damper system. So the equation usually goes like this. F is equal to ma plus cv, ma plus cv plus kx. So this is the simplified equation of a spring system with the dampener. Now I'm going to modify this equation a bit. Like what I'm going to do is I'm going to bring this ma to the left side and I'm going to take this force to the right hand side. So this equation becomes ma equals to the f stays there it is and the cv comes to the left hand side. So it becomes minus cv and this kx becomes minus kx. Now what I'm going to do is I'm going to bring that m to the right hand side. So this equation becomes a equals to 1 by m into f minus cv and minus kx. So this is the final equation that we are going to simulate. So in this equation, a is the acceleration. So a equals to acceleration and v is the velocity. X is the displacement. And the other components are m is a constant which is mass. C is the damping coefficient. This is an important term because the damping, the how much the spring gets damped, it depends on this damping coefficient. And the K is the spring constant. So these are the variables on the constants present in our equation. So we will be using these. And before getting into the simulation, I would like to remind you that the velocity is nothing but the integration of acceleration is the velocity. Similarly, integration of velocity is displacement. So these are the basic things that we need to know. And one more thing is, for the simulation being, we are going to assume the value of spring constant k as 2 and the value of c. Now based on the question, for an underdamped system there is no damping, so let's keep the value of c as 0, which means there is necessarily no damping occurs. For an overdamped system, let's keep the value of c as 0.5 or 1 based on your requirement. You can change the value of c in the simulation. So let's keep it as 0.5 and let's proceed to the simulation. So open the library. Now for the as per our equation, I am going to simulate it from the from the right hand side, left hand side. So first what we have, from the right hand side. So I am going to simulate this equation. So first on the right hand side, inside the bracket we have f, cv and kx. So for f, I am going to use a constant block now. So go to commonly used block and drag a constant block inside. So I'm going to rename this constant block as force. So wait for it to appear, and now click on the constant block and rename it as force. Now we have two more two more variables on the right hand side, which are cv and kx inside the bracket. After f we have cv and kx. Now v is velocity, which we don't have yet, and x is displacement, which is also a variable and we don't know what it is. But however, we have the values of c and k. So to represent the value of c and k, I am going to use a block known as gain block. So this gain block is essentially nothing but it is a multiplier block. Like, consider this equation, we have cv and kx, out of which v is a variable and c is a multiplier. So to represent c, I am going to be using a gain block. Similarly, to represent this k, I am going to use another gain block. So I am dragging two gain blocks inside. So one gain block, I am renaming it as c, which is a damping coefficient, and another gain block I am renaming it as k, which is a spring constant. So like I discussed, let us keep the value of spring constant as 2. You can keep any value. I am assuming the value of 2 for my simulation. And now we have all the three here aligned. So now we have to subtract c and k from force. So to do that, I am going to use a subtract block. So subtract block is found in math operations. So in math operations, click the drop down menu and you'll find this various blocks. So locate the subtract block. So subtract block is here, but there is only 2 ports in this block. But however, I have three variables to give it as an input. So what I'm going to do is I'm double clicking it, and in the list of signs I'm going to add one more sign, which is a negative, and click OK. So now as you can see, the subtract block has 3 variables. So let's do it. So as per our equation, force is a positive variable. So I'm dragging the force to the positive port, remaining I'm dragging it to the negative port. So now we have the basic variables inside the bracket. Now outside the bracket we have a term 1 by m. So I'm going to consider this 1 by m as a it is a multiplier. It's a constant multiplier. So I'm going to use a gain block once again. So go to commonly used blocks and drag a gain block inside the workspace. So I'm going to rename this gain block. Don't need to change the value. Let it be 1, and let's rename the gain block as 1 by m. So this way we have completed the right hand side of the equation. So this half part of the equation is complete. And what is the value of this equation? The output of this equation is an acceleration. So now what we have here, the output which we get from this port is an acceleration. So like I said, we need velocity and displacement. So to get velocity and displacement from acceleration, I am going to integrate this acceleration using a integrator block. So in the integrator block, check if the integrator block is present in the the commonly used block, and here we have integrator block. Just pull the integrator block inside. I need 2 integrator blocks, and so I'm pulling 2 here. So the first block I'm renaming it as velocity, and the second block I'm renaming it as displacement. So now I'm connecting the gain block, the output of the gain block to the velocity here. So just pull it here, and I'm connecting the output of velocity to another integrator which gives me displacement. So now as per the equation, the velocity is multiplied by c. So what I'm going to do is I'm going to drag the output of velocity and give it as an input to the gain block of c. And similarly, I'm going to drag the output of displacement and going to give it as the input of spring constant K. So this satisfies our equation, which means Vc minus Kx. So now we have completed the simulation almost. So now to view the output of the simulation, we can either use a mux block to combine both velocity and displacement, or we can use separate scope blocks for velocity and displacement separately. So I'm going to use a mux block here. So like I said in my previous tutorials, mux block essentially combines two signals. So for one input, I'm going to drag the velocity and give it as one input, and for another input, I'm going to drag the displacement and give it as another input. And to finally visualize both the input in the same graph, I'm going to use a scope block. So connect the output of the mux block to the scope block. And now we are ready. So now let's run the simulation. So as you can see, the simulation is currently running and it's compiling. So once the simulation is done, let's click on the scope block to visualize the the end simulation of velocity and displacement. So now as you can see, the velocity starts at 0. It is a gradual sine wave. However, after certain time, the wave becomes numb and becomes a flat line. Same as the wave of displacement as well. So if you want to know which is displacement and which is velocity, just enable legend and you can see the velocity and displacement here. So like I said before, it starts as a uniform wave, but it becomes a flat line over a period of time. This is due to the fact that we have given the value of damping coefficient as 1. So let's try 0.5 here to see how the velocity and displacement vary. So I'm clicking on the block and now you can see it starts as a wave, uniform wave, and it is still a wave at the second interval, but only after that it becomes a flat line. So now this is a generally damped one. The previous one is an overdamped oscillation. So now finally let's give an underdamped oscillation to this. So I'm going to give the value of CS0 and I'm going to run the simulation. So as per our theory, yeah, now the scope we can see it as this is a uniform sine wave. So this is a uniform curve, a sine wave curve, which is produced by the displacement of the shock absorber spring. So from these you can conclude that this is the simulation of our question. As per our question, this is the shock absorber system simulation, and we have simulated it for both underdamped and overdamped oscillations. So thank you, friends.